I'm sorry.
This is after I got lost in two labyrinths this morning. You go into the cafeteria there, and nothing's ever in the same place. And then if you look at the buildings around here, they all look identical. I mean, it's easy to make a wrong turn. Okay, so I have two bonds here. We're in two dimensions right now. Two dimensions, not one dimension, right? We could do one dimension. Okay, so here I have the directions along the bonds. The B1 is just the unit vector along the y direction. This is y, and this is x. And the next one's the same thing. B2 is also EY. So that's the unit vector, There aren't enough symbols in the world. People who think there are enough symbols in the world to do everything write books where the first 3 pages are nothing but lists of what the symbols are. I don't know if any of you have ever looked at Truesdale's book on mechanics. Literally, the first 4 pages are telling you what symbols he's going to use, and heaven forbid he should use the same symbol for different things. And so he has to use Roman alphabet, italic, bold, and then he has to use the Greek alphabet. And then he has to use the Russian alphabet. He used the Israeli alphabet, the Hebrew alphabet, and there's one other, 4 of them, and you didn't even know what to call the symbols. So you can live with having things called the same thing. So this is the extension of bond 1. It is EY, because that's B1, dotted into the displacement. So what happens when I extend this? I move the 1 upward, and that causes the length of this to change. So E positive means it's changed. So this is just dotted into U1. Okay. Now I look at the extension of 2. The bond's in the same direction, but now when I move this upward, I decrease the length of the bond. So I have here minus dot U1. Okay. So that means now I can write a 2x2 matrix C. So just to be clear here, this is E1 equals U1y, E2 equals U1y with a minus sign. And if I make this the x and this the y, nothing happens to the x component on this. And then I have a 1 and a minus 1. And you can clearly see from this that there is a 0 mode. See, I'm talking about a 0 mode if ux. Well, let's go on and write this out just to be clear. So this is u1x, and this is u1y. And so this is equal to u1y minus u1y. And you can see that we have a 0 mode no matter what u1x is. We don't. So if we move u1x, in other words, if we move this thing back and forth a little bit to the linear order, we don't change the length of the bonds. So we have here 1, 0 mode. Then we can take the transpose, which is 0, 1, 0, minus 1. And this would be the tension. I multiply this times the tensions T1 and T2. And that's equal to 0, T1 minus T2. So when I operate with Q on that, so you can see that the 0 mode corresponds to T1 equals T2, which is just what I've been telling you. If the tensions in these two things are the same, I mean the state of self-stress, the tensions in these two things are the same, the force there is 0. So you can see now that when I write it this way, the fact that it can support stresses means that I can move these things up and down and still have a 0 force there, which means that I can put the system in a state of stress. But it doesn't have to be there. Now you can do the same thing. Oh, I guess one should do the count here. So the number of 0 modes minus the number of states of self-stress should equal dn minus nb. So we have one site, n is 1, the dimension is 2, so we have 2 minus 2 is equal to 0, as it should be. So I invite you now to, as a homework problem, if you wish, to put this under periodic boundary conditions where you identify this one with this one. Then we have two sites and two bonds, and write out the equations and see what happens, and you'll find you also get a state of self-stress.
So is the effective potential for your zero mode actually quartic? If I look at the horizontal displacement?
There is the displacement here comes out to be, it's quadratic in the displacement. In other words, the change in length in this guy is quadratic in that displacement. Well, the energy I'm considering now is just quadratic in the displacement, which means that these things have zero energy. In reality, there are. That is correct. Yeah, there is a but the real spring that then, if you go beyond that, then you have to worry about that. Yeah. So, but I'm looking at the linearized case. Okay, so that's confusion 1. Confusion 2. Some of you were worried about the fact that I wrote the elastic energy as a half k sum over beta E beta squared, and I was saying that the E betas are independent. Well, they're independent in the sense if you give me each E beta, I have the total energy. But you can ask the question, how are these guys related to the displacements? And since we have E beta is equal to C times U, well, capital E, well, you know what I mean. So I can always convert this to U. And the question is, do I have all of the information with the E betas alone? And I don't, because usually in the things we look at, the number of bonds is greater than the number of sites. And this matrix then becomes a non-invertible matrix. And if I just give you the bonds, I don't know what the displacements are. So what I want to do is to put it back in terms of U. Now, the Maxwell lattices we're looking at, I hadn't appreciated this until I thought about it. This is a square lattice. And as long as there are no zero modes, as long as the spectrum is gapped, then we can actually invert this. And indeed, you can use then for statistical mechanics calculations either E beta or U for the special case where this is a square matrix that is invertible, which means it has no zero modes. Okay. Now, the final thing has to do with affine response. So under affine response, we set the position of the nth lattice site equal to a lambda times its rest position. And this is the same for every lattice site. Okay, this matrix here, this deformation matrix. So we have then that this is equal to RL plus UL. So UL under affine displacements is lambda minus 1 on RL. Okay? And I'll just call that eta RL. So the stretch of a bond is B hat beta dotted into U of S beta prime minus U of S beta. And both of these things have an eta in it. So this becomes dotted into eta, which is a matrix, times R of S beta prime minus R of S beta. These are the rest vectors of sites beta prime, S beta prime and S beta. And this difference is nothing more than B beta, because that's the definition. So E beta, you start off with, if you have a fine response, then for every, this doesn't have a hat on it and this has a hat. So for every bond, you do this. So you put that into your calculator, and then you say, with that constraint, I'm going to now allow all of the sites to relax until there's no force on them. And that gives you the real response. Okay. So when I told you that we have that the elastic energy was 1/2 K times E of fine, well, E of fine, right, dotted into the vectors that span the null space of Q, squared and summed. This E of fine is the set of vectors defined like that. And then these are the things that you've calculated. And you have to have, it has to be non-zero overlap between this guy and the affine displacement in order for this to contribute to the elastic energy. And there are some cases, if you take the square lattice, for example, and do this to it. So I'm going to do and keep on going like that. So we've sheared every other thing. Then it turns out that there actually are states of self-stress that involve two of these things, in which the signs of the stresses vary, and you can't support a stress this way because they don't have an overlap with the affine response. And you can tell clearly if I have this and I press on it, then all I'm going to do is to collapse the thing. OK. I think those are the ones that I need to go about. Now, we're going to managed to get my things out of order here. 3, 4, 5, 6. OK. So now we want to return to gee, I thought I had started this from the current slide. OK. So we're going to go back to the square lattice. No, we're not going back to the square lattice. OK, well, we talked about the square lattice last time. And why did I pick this up? It's to make sure that you're listening. So the only thing I didn't talk about with the square lattice, we counted the number of zero modes. We found we had these knife edges in the Brillouin zone. But now let me take the lattice which is periodic, which means that at some point this guy's identified with that guy. Or let me go one further up. I have these set of bonds here, and these sites, and I don't think so. On mine? No, it should be the same. Am I not plugged in? Did I grab the right one? Maybe I grabbed the wrong one. There we go. OK. So remember that we have nx bonds in this direction, or nx rows going along like that, nx columns, right? And that means that we have, along this direction, we have one mode per site, basically. Now I come along here and I cut these bonds there. And I leave the others under periodic boundary conditions. So I've reduced the number of bonds by nx. And in the process, I've removed all of the states of self-stress that came along these lines, because they're no longer connected. They're just free there. So that means that my number of zero modes now, remember I had this. So this is now equal to nx, because I started off with it 0, and I cut nx of them. And this guy has one less thing. This is now just the ny, because I've removed all of the zero. This is nx. No, it's ny, because I still have the states of self-stress. And when I do this, it's going to get into the confusion between the x's and the y's. I thought I had it figured out this morning. We have a lot to cover, so just be convinced here that I've cut n of these things, and I've removed n states of self-stress, or nx states of self-stress, and by removing the bonds, I've increased this side by the same amount, and the net result is that I have the same number of zero modes, because I've decreased this by nx, and I've decreased this by nx. So I end up with the same number of zero modes. And that means that all of the modes are contained in the spectrum of the bulk. And if I try to come in here and do a Rayleigh wave on the surface, what happens is I just push this thing all the way down, and I get the same Rayleigh wave down here. In other words, if I had a surface mode, you could call this a surface mode, but it's a surface mode of infinite penetration depth because it goes all the way across the sample. Okay? So that's telling us that this lattice is a little bit special. Okay, so let's now go to the Kagame lattice. Now we have, ignore the red lines, we have these straight lines that go in 3 directions. So that means we have more states of self-stress, and we have 0 modes all along the boundaries going from gamma to m, or the line going from gamma to m, and the 3 equivalent versions of it, because we have these 3 lines, each of which have states of self-stress, 1 for every line. So there's 1 for every q going along those lines there. Okay? In addition, because at q equals 0 now, we have 3 states of self-stress going in the right directions. You have now three positive definite eigenvectors, eigenvalues of the Voigt matrix, which means that elastically the system is stable. The square lattice had this shear mode which cost us no energy. Now, at least to linear order, all of these distortions of the lattice cost you energy. But the peculiar thing is the price you've paid is you have an extra 0 mode at q equals 0, which is a phonon-like mode that wasn't there before. So it's sort of curious in this argument. You strengthen one part of the system, but you weaken another part. So at q equals 0 now, we have 3 states of self-stress, which means we have to have 3 0 modes. The standard picture would be you only have 2 0 modes because of the translation. So there's an extra q equals 0, quote, floppy mode in there. So because we have 3 states of self-stress, we're elastically stable with respect to the spatially uniform distortions, but there's an extra phonon-like mode at q equals 0, a floppy mode.
And rotation doesn't count.
Rotations don't count because it's periodic boundary conditions, right? This is k prime equals 0. We don't have the next nearest neighbors. Okay, obviously I don't have the time to go through all of that. If we look at the spectrum here, there's this line of zeros. If we add next nearest neighbors, we gap the spectrum. And you can see here are the 2 phonon modes, the standard phonon modes. Remember, when all of our standard acoustic modes are going to be non-zero because I've got a standard isotropic elastic system which I can use to calculate the standard acoustic modes. But there's this extra mode rolling along here at q equals 0, which is the one that, it's the extra one. It's gap. By gap I mean everything but the origin. The origin has to have a 0 because of the translational invariance, but everything else is gapped over here.
For non-zero k prime, there's always a wave vector that will work. The energy gap per se is high.
No, there's a gap right here. I mean, this is a finite. That's a finite energy.
Wave vector is a gap.
Yeah.
But usually, Ashcroft-Furman,
Yeah.
I remember it, a gap is where there are no wave vectors, no bulk wave vectors allowed. If I look at your middle plot, there's a red line sliding up near the origin. So for any energy with a wave vector that would work. But slide horizontally,
Yeah, in that sense. But if I come down here, I don't. There is a wave vector. Okay, if you use it that way. But what I mean here is that there is every energy is greater than 0 except that one. Or
very high energies with the conventional gap, you're well above the green.
yeah, these guys are the conventional ones. If you want to talk about that, right? Well, no, not even there because here I go. Up, still has it.
You double the energy.
Yeah. Okay, I'm using the term gap to mean right now, okay, and I think it's the appropriate use right here. Okay, now I want to go to the twisted Kagame. I should say that the standard Kagame has the same thing about the surface modes. There are no surface modes. They have infinite penetration depth. Now, by doing this simple transformation, going from here to here, all I've done is to counter-rotate these triangles. So I rotate this one this way and this one this way, you get that, and so forth all the way around. And I preserve the threefold symmetry. So now I have a lattice which has the same number of bonds and sites, but no straight lines going across. So I've lost all of those states of self-stress which are associated with the straight lines, which means that I've lost all the zero modes that went there. So carrying out this simple operation means that I no longer have zero modes running along the symmetry directions. And in fact, the spectrum looks almost identical to the spectrum of the one where I add next nearest neighbor. So this is the standard Kagame lattice. This is what happens when I add a next nearest neighbor. And this is what happens when I twist it. So just by this geometric operation, in my language, I've gapped the spectrum. Right? Yes?
Make sure when you're talking about the states of self-stress, that's like that.
Yes, exactly. I mean, when you have straight lines, you always have these load-bearing states of self-stress.
Zero mode free time is what you talk about.
Yeah, right, right. And those zero modes, they no longer exist. Yeah.
What's the difference qualitatively between lower left and upper right?
Lower left. Well, qualitatively, there's no difference. In other words, twisting the lattice in terms of the bulk spectrum has the same effect as adding next nearest neighbor bonds in terms of the spectrum. Right? That's remarkable in a sense.
Should be comparing to the upper left, to the kind of.
Yeah, this is the one that's the same for both. I twist, I go that way, I add bonds that way.
But no next nearest neighbor.
No next nearest neighbors, right. And you can calculate what the gap is. This gap is sort of the maximum one that you get, and that thing scales like the sine of the twist angle. So when the twist angle goes to 0, the gap goes back to 0, and that thing goes to a straight line. Okay. So now we can ask, well, okay, so one thing is now we've lost the 3 states of self-stress at q equals 0, but we still have 2 states because the translational invariance requires that I have 2 zero modes at q equals 0. That's these 2 guys. So I still have 2 load-bearing states of self-stress, which means that I have 1 guessed mode. Remember, the guessed mode is the mode instability of the elastic system. And the guessed mode is what you can see here. I'm going from here to here to here to here. I don't change the length of any bond in that process. So what I do when I go from here to here is what? Changing the area. So this tells us that the bulk modulus is 0. Now, what do we know when we have a system that has a 0 bulk modulus? Lecture 2. The surface mode has 0 energy. The Rayleigh wave has 0 energy. So, and in fact, that has to happen now because once I cut the bonds, remember in the argument over there, I reduce the number of bonds and I reduce the number of states of self-stress at the same time. Now I have no states of self-stress, basically. I reduce the number of bonds, so I still have to have the same number of zero modes as I had before I cut. And those modes are surface modes. Before I show you that, let me just switch and show you. I want to show you a quick movie. So these materials so this is a real twisted Kagame lattice made from, I forget what the material is, but it's a fairly soft material. And we're just applying a stress up there. And look what's happening. Exactly what I showed you in the picture. I mean, it's not perfect. This is not exactly the same thing I've been talking about because there's residual bending energy in these things. But it's still a negative Poisson ratio system. I push on it like that, and it squeezes in the other direction. Okay. Now we can go back to our demonstration here. And so now I would like to talk a little bit about how we actually calculate. So you'd like a method of knowing, for sure there's going to be an accident here. Let's see. How do we actually go about calculating the zero modes? Now, the thing is we know we have zero modes. The general process of calculating the surface dispersions is not totally trivial. I mean, if I have next nearest neighbor forces and so forth, it's something of an algebraic mess. But here we've got an easier task because we know if we have zero modes, they have to correspond to zero modes of the compatibility matrix. So all I have to do is to show that there's an eigenvector such that when the such that when the compatibility matrix operates on it, I get 0. So the first thing I need to do, here we have a system that has 3 sites in the unit cell. Let me just see here if I've... Yeah, just a second. So, you know, your first inclination is to choose a unit cell that has 6 bonds and 3 sites such that it retains the symmetry of the lattice. So these are the ones that you would want to put in. But these are not compatible with the surface. So you want to choose unit cells that are compatible with the surface, which means that all of the bonds and all of the sites lie within the surface, and I don't have things dangling out at the end that aren't there. So this unit cell is perfectly good. This is a perfectly good unit cell. This is a perfectly good unit cell. And you want to choose the unit cell so that it matches the boundary. So if I do that, then if I calculate the compatibility matrix, I have, you know, a relation between the bonds and the sites within the cell. And then this bond connects me this site to that site. So that means that I'm connecting things one cell deeper into the lattice. And the compatibility matrix then breaks up into something of the following form. Ooh, now we have a nasty piece of chalk that has a much different coefficient of friction. I don't like that one. It's sort of like rubbing your fingernail over it. This one's better. So the compatibility matrix breaks down into this block diagonal form. C11 is that part of the compatibility matrix that works only within the cell. And then there's a C12 that takes me to the next cell up. And then all of the rest of them are 0. And then we have this. Etc. And in the lattices we're looking at, all of these are the same, but you could imagine coming along and making this one a little different. But the point is that we now have something that is C11 UN plus C12 UN plus 1 equals 0. And you look for solutions in which UN plus 1 is equal to lambda UN, where lambda is less than 1. Magnitude lambda is less than 1. In general, lambda can be a complex number. Yeah?
We have matrix that looks like this because the bounds are reaching into the next.
That's right, because I'm writing the full thing, but as I move like this, I have a set that keep me within the same cell, and they only connect to the cell above. I don't have any of these connections to the cell below. And so now all we have to do is take the determinant of this guy. Excuse me? Do I have a tau lambda? Oh, these are zeros? Oh, this is 0. This chalk really has a funny feel to it. We'll blame it on the chalk. And I have I'm sorry, I wrote this wrong. What happened to all the erasers? They're hidden here. Here we go. That's correct. So this thing operating on U gives me the extensions. If it's 0, the extensions are 0, and I have a 0 mode because it costs no energy, right? So I take the determinant of this. Now, remember, we are under periodic boundary conditions, so I have a matrix for each wave number q along this direction, okay? And the matrix is simply a 6 by 6 matrix here because there are 6 bonds and 6 sites, and for each q, there's a 6 by 6 matrix. So now I've reduced the problem to something that is manageable. You solve this, and if you find that lambdas are magnitude less than 1, you have a solution penetrating into the bulk. And what happens is if we look at cuts along, I mean, you can cut the lattice in many different ways. But I'm just going to look for the moment at what happens if I cut the lattice this way or if I cut the lattice this way. So you see, if I cut it this way, I cut 2 bonds per unit cell in order to remove the system from the periodic boundary conditions. So you can think of these things are bonds that would have connected down here. You know, this one connects to somewhere down there. I cut it, and now I freed the thing completely along a strip. And what happens now, you don't know, the counting argument, the Maxwell counting argument, or the generalized index theorem, does not tell us where these zero surface modes are. All we know is they have to be there because of the count. And it turns out in this system, we always have, here we've cut 2 bonds. There are going to be 2 zero modes per wave vector along that direction, or wave number along that direction. And it turns out that you always have 1 here and 1 here for this system. And here we can draw what they are. This is the real part of the penetration depth, inverse penetration depth. I write lambda as e to the minus kappa. And this is for different values of the angle as a function of the wave number in the plane. And you can see that for small angle, the thing asymptotes to something here. And it turns out that it asymptotes here to a length, an inverse length, which goes like sine of theta. So as theta gets smaller and smaller, this guy, the inverse penetration is smaller, so the penetration length gets larger and larger. And this one has to do with special properties when I go up to a large theta. There's another one down here where kappa r is negative, which tells you that I go from the top surface down again. Now here, the unit cell looks like this. And in order to get there, I have to cut 4 bonds. So I have to have a total of 4 zero modes per Q. And here I've shown you what the kappa r looks like. Notice that there are 2 positive ones and 2 negative ones. The positive tells me that I'm decaying upward, and the negative says I'm decaying downward. So that means I have 2 modes on each side. But notice that there is an asymmetry, even though the count is the same. Up here, what's down here looks exactly like that. Here I have really totally different magnitudes for them. But all of them, we reach the limit that we get from doing the Rayleigh wave calculation with the continuous variables. Okay? So, now, you've all heard about topological insulators, and some of you may have heard about polyacetylene. When you have systems where you have a symmetric state that can break up by a phase transition into equivalent states with opposite symmetry, you often gap the spectrum in the electronic sense that David was talking about, and associated with that gap is a zero mode. So there's a natural question to ask here. Is the Kagame lattice with all of these lines of zero modes the analog of, quote, the high temperature phase that hasn't broken the symmetry, and this phase, the lower one, where I've gapped it, should there not be some kind of topological characterization that we talk about? The trouble is we only have this lattice at the moment. We need something else to see whether or not it happens. So I'm going to start with a one-dimensional model, which... So the Su-Schrieffer-Heeger model is a spiral transition, and that's the simplest model, right? And that in fact is the canonical one that everybody looks at and was, beat to death in the 70s. So that's that thing, right there. Well, but the topological properties was the 70s, right? That was the. So excuse me. Well, that one's a funny thing. There you get. I mean, if you mean the pure Frankel Contour where I've got the washboard and I put things on top of it, well, I guess if you get one of the commensurate states, that might be, but I'm not sure that I have 2 directions for that. They can fold right, yeah. So I guess that may be the case. I haven't looked at that one, but that's possible.
This commensuration from that model,
yeah.
not perhaps in a topological way,
80s, yes, right. They were beat to death in the 80s, yes, I know.
A lot of dead things lying
Mr. Perbach and others, right.
around. Life left.
It also appears in a well-known textbook treatment of it, because it was done in the 80s, yeah.
Could that be Chicken and Lubensky by any chance?
Who are those guys? I don't know. My guess is no also, but I haven't looked at it carefully enough to be sure. Right? So I will be in your camp, and somebody can solve it for us. Anyhow, this is polyacetylene. You have carbon atoms, and then associated with the carbon atoms, you have hydrogens coming off. And you can imagine a state where you've not dimerized. So here's a chemical picture of the polyacetylene, where you double have, in order, there's one hydrogen coming down, the carbons have valence 4, so I need to have 4 bonds coming in, and you adopt this alternating structure, and obviously I could change and put the double bond here and the single bond there. So now I'm going to give you, we could spend a lot of time doing the arithmetic for that model in particular. Instead, I'm going to look at this model that Charlie Kane dreamed up, which is a mechanical model whose Hamiltonian really is essentially identical to this. Okay, and it has.
Between the squares and the blue dots are simply the two sublattices?
That's correct. Yeah. They're all carbons. Yeah. So I'm going to take a rigid rod down here, attach to them rigid bars that go up and down and up and down, and then I attach the ends with springs. Okay. So in this state, it turns out that you have lots of zero modes where you can move this guy this way or that guy that way and not change the lengths to the order in question. No. No, I said that wrong. I have a zero mode where I can click all of them over. But now if you tilt this way, what you're supposed to do is to identify the red carbon with the bond and the blue carbon with the site. Okay. And okay, so now I need to write down some things. And this is the part where I don't know how well things are going to go unless I have 2 more hours. But I'll try to give it to you. So I'm going to write down, there are 2 springs that hit each site. So I want to write down what is the compatibility matrix. First thing I want to note is that this thing does not have translational invariance, right? It's locked to the rod, so I'm not required to have any zero modes by the symmetry, right? So twisted Kagame ladder. So we have schematically, we have sites. This is site 1, site 2, site 3, etc. And we have bonds, etc. Okay. And I want to know, and the only degree of freedom each of these things has is the freedom to change this angle. So again, I have something which is morally equivalent to a string of sites connected by bonds. So I'm going to look at what is C beta S. So this is the component of the compatibility matrix which links the bond beta to the 2 sites S on either side of it. And you can do the arithmetic, which is in the version of the review article that you have. Okay, and C1 and 2 have the following form. Okay, I should tell you that this distance is A, and this length is R. Okay, so the distance between the sites is A, and this is equal to A plus or minus 2R sine of theta bar R cos theta bar over the square root of A squared plus 4R squared sine squared theta, where theta bar is the tilt. So here you can see that we have to go from here to here. What I've done is tilted every rod. So let's see. Yeah, every rod in the same direction. So the top one tilts that way. The bottom one tilts that way. So it looks like you're rotating with opposite angles. So I could either do it that way with a positive theta bar, or I could tilt them all this way with a negative theta bar. So I have two different possible ways of breaking the symmetry. And you can see that what happens here, that when sine of theta bar is equal to a over 2r, then one of these things becomes 0. So we can take the Fourier transform of this. This is equal to minus c1 plus e to the I qa times c2. And this is operating in the forward direction, if you wish. So I get a 0 mode if I can convert this at a surface. I mean, I should say that if we put this all together, we have a spectrum which is plus or minus c1 minus c2 squared plus 4c1 c2 sine squared qa over 2. And you can see that this spectrum is essentially fully gapped unless c1 equals c2. If c1 equals c2, this thing becomes proportional to sine of qa. So at q equals 0, we have a 0 mode, the 1, 0 mode, right? So here, this tells me what happens if I have q's that are real. But if I can find a solution where this thing is equal to 0, where q is equal to I kappa, and rather q is equal to I kappa, and e to the I qa is equal to e to the minus kappa a, then we have a solution in which we have a decay of the magnitude going towards positive values of x. And you can see what happens here. Let me just call this thing lambda let me call this z. Call this z for reasons which will become evident in a minute. This says that we have a 0 mode if z is equal to c1 over c2, right? And if magnitude of z is less than 1, then as we go forward, the amplitude decays. So if c1 is less than c2, then we have a 0 mode starting at the right-hand side, which is a surface mode. If c1 is greater than c2, then we have a 0 mode starting at the other side coming in. So depending upon what the relative magnitudes of these two things are, we either have a 0 mode at the right end or a 0 mode at the left end. And we have, as you can see here, we have that the number of bonds is equal to, actually the number of sites is equal to the number of bonds plus 1 in this particular thing. So the number of 0 modes is equal to 1 because we don't have any states of self-stress. So I have to have one 0 mode. When q is equal to 0, it's the 1, 0 mode that extends across the whole sample. So that's something like being in the hexagon, the untwisted Kagame lattice. But if c1 is not equal to c2, that 0 mode either resides on the right side or the left side. Okay? And we have this relation that relates, so that the information about whether or not we have the 0 mode appears in the C of q, which tells us something. This guy gives us what the spectrum is, because the omega squared is the magnitude. I should have said this is equal to magnitude of CQ squared. So contained within the spectrum of the bulk sample is information about whether or not we have the 0 modes. And that's where the topology comes in. So make sure I write this correctly. So there's something called the, this is one of Cauchy's theorems. I forget exactly which one it's called. So let's take any function or meromorphic function f is a function of z. Yes?
Sorry, just to clarify. So you look at the zeros of this particular matrix.
Yeah.
You could also look at dynamic matrix.
Right.
This has more information.
Okay, so there's so much to do here. So in quantum mechanics, you have a Hamiltonian which looks like this. Let's see, I have a C dagger here and a C here and a 0 here. And this guy is connecting the A sublattice to the B sublattice. Okay. Now, for us, what we have is H equals this H squared. So this part right up here is our dynamical matrix. And so what we're doing is we are thinking about the problem in terms of this representation, in other words, the square root of the Hamiltonian, if you wish, because this guy alone doesn't have any phase information in it. So I need something, if I'm going to talk about the topological properties, I need something that has phases in it. So this guy has phases, this guy doesn't. Well, H squared has this part here. Well, if I look at the zero modes which correspond to the, there certainly are zero modes which correspond to this guy being 0. Right? Because, and then there are additional ones, but these are the self-stresses. So this guy has a Hamiltonian which gives me both the zeros of the self-stress that come from the zeros of C dagger and the zeros of C. Yeah. No, I mean, no. Look, see, this guy only operates on the block in which I have the sites part here. So if I set if I have no bonds here, and I just have something where the C operating on the sites gives me 0, and I set all of the bond variables equal to 0, I'm okay, right? So this has more information, but it has in it a problem that is another problem that we don't. Okay. I mean, really what we need is some way of mapping our problem onto, in our case, the complex plane. Yeah. Right. So this guy has the 0 modes associated with displacements. This guy has the 0 modes associated with the tensions in the bonds. Okay. Correct. And so when you look at it this way, this guy couples bonds to sites, and it turns out that when you look at the 0 mode there, what happens, so that it depends on how you terminate your thing. If I terminate with the double bond, what happens is the displacement or the electron occupation of every other site is actually 0, but that's telling us that the bonds don't stretch. So there are a lot of these analogies which take a lot of time to deal with. So maybe we can spend a little time later on talking about that.
I have a philosophical question. Maybe you just comment briefly, or you can say it's out of order if you like.
It's out of order. No, go on.
So we talked last time, and you explained how to put in finite temperature and so forth.
Yeah.
What happens to these 0 modes when you have real quantum mechanics? 0-point motion.
They probably go away. I've not yet investigated that. That's a good. I mean, it's a question we've thought about, but not enough detail that I can answer it.
Thank you.
Good question. Yeah. Okay, so where am I? Right. So I want to say if I have any function and I do the following. Does anybody know what that equals? Okay, this is equal to the number of zeros minus the number of poles inside this contour. Okay, so if I have a function that has no poles, I can throw this away, and this integral tells me how many zeros I have of z lying within the contour. So suppose I now take the contour integral 1 over 2 pi integral over magnitude z equals 1 of dz of d log of c of z dz. What's that going to do? That's going to count the number of zeros that lie within the unit circle in the complex plane. If I have a zero that lies within the unit circle, its magnitude is automatically less than 1, and therefore I've counted for you the number of possible modes that I have that will penetrate from the left to the right into the system. If I had it the other way around, so I just use this as a number. So for our case, if C1 is less than C2, then we have a pole in there, a zero, right? If C1 is greater than C2, there's a zero that sits out here, which we don't count. So that means that by looking at this number, this topological number, for our case, we either get 0 or 1. And if I get 0, that corresponds to having a 0 mode on the other side. And if I get 1, I have a 0 mode on the left side. Right? So this tells us that by doing this topological integral, if you wish, which is this integral, incidentally, okay, I need one more step. Z, recall, in our case, is e to the iqa. So I can convert this integral into a 1 over 2 pi I, integral 0 to 2 pi over a, dq, d log q dq. And that's the same thing. And when I integrate from 0 to 2 pi, I'm going from between two equivalent points in the Brillouin zone, which means that in essence, I'm doing an integral around the circle. Okay, so this gives us the 0 mode. We know from our count that we have to have one 0 mode. So we either have the case where the 0 mode is all the way across the sample, it's on the right side, or the left side. Now, it turns out that this also implies that if we mix the two together and get a domain wall that separates a theta plus, a theta positive from a theta negative, then we have, if I look at this, we have something going to the left, which if we create it so that if I cut this right here, there's a 0 mode going in this direction, we know what that 0 mode looks like. If we cut it this way, we've got a 0 mode going in the opposite direction, and we have an amplitude for each of those. Now I need to connect these two together to create my domain wall. Now here's one way of doing it. I connect it together by adding one site and two bonds. So what we can do, and to ask whether or not we have a 0 mode here, is to look at this collection right here and ask for this grouping, what is the compatibility matrix associated with this. So there we have one bond, one site, and two bonds. Okay. This site has 1 degree of freedom, and I have 1 degree of freedom, which is the amplitude of the decaying mode in that direction. So I know that if I give this and I allow it to decay with the calculation I've done for the free surface, I've got every bond down in this direction is unstretched. I do the same thing here. Every bond in that direction is unstretched. And I have some amplitude, which I need to determine for each of those. So I have 3 amplitudes rather, I have three different variables, the rotation of this guy and the amplitude of that, and I have to use that to fix the length of two bonds. And I know I have no states of self-stress, so if we look at this thing, it turns out that there's one and only one zero mode there. Or I could alternatively have connected it like this. I didn't draw it in the picture. Then I only have one bond, but I have two independent variables. But remember, the overall magnitude of the two doesn't matter, so really I just have the ratio. I have one variable that can match the constraint of this. So there's a counting argument. If we know how many zero modes we have going this way, we know how many amplitudes we have in that direction, we have the number in that direction, and we're guaranteed to get a zero mode in the middle. Now, if you look at the literature on this, there's some much fancier ways of showing it, and you know, in the appendix, rather in our original nature physics paper, in the appendix or the supplementary material, we derive it in a more, quote, mathematical way. But really, all of the physics is in this counting. Okay. So now what have we got? We have two-dimensional lattices where we found that if we gap the spectrum, we necessarily have zero modes on either side. And we found that for the simple case, the zero modes are equally distributed between the two sides. Now we have an example where we have only one zero mode in the whole system. And by changing the geometry, in a sense, we can move the zero mode from one side to the other. So the question is, can we create lattices which obey the Maxwell count, but in which I move zero modes from one side to the other? And in that case, I would have a topological characterization. And the answer is we can. So to simplify things, remember that the Kagame lattice had three sets of parallel lines. So we're going to distort the Kagame lattice, so I only have a set of parallel lines in one direction. Makes it simpler to think about. So the parallel lines in this direction give me states of self-stress along here and a line of zero modes like that. And now I want to do the same sort of thing that we did for the polyacetylene, which is I want to distort the lattice so that we get rid of this straight line and we have things that look different on the two sides. So this going this direction, we get the Kagame lattice and we have the gapless spectrum. Going this way, we have another lattice that, notice this lattice has an asymmetry to it now, which was not present there. You might say, it looks like I have a geometric dipole. And in the end, we'll show that there's a topological dipole associated with this. And if you look at the spectrum, you might say, looks like I've got zero modes here. The dark part means that I have, low energy modes. It turns out that these guys are not zero modes. They're modes where the frequency goes as omega squared instead of omega. Yeah, omega squared goes, omega goes as q squared instead of q. And that form is a consequence of the fact that over on this side, all of these have guessed modes because we're gapped completely. So the guessed mode over here is the overall compression. We have a negative Poisson ratio system. It's auxetic. And it turns out over here we have a positive Poisson ratio system. And it's that difference which changes the long wavelength behavior because the elastic energy determines completely the long wavelength energy. Now, the description of these is a little bit arcane, to tell you how we collected the number. I certainly don't have time to do that. But I can tell you what the answer is. So the expectation is, as usual, I don't have the things in the right order. What happened to my ordered things here? I'm sure I started off with 8 pages. Did I lose something somewhere? 5, 6, 7. Okay, we have 7 pages at least. So now I'm just going to tell you results because they're really, the derivation is a little tedious. How am I doing? So I've gone an hour. Do we want to take a 5-minute break? I probably have 45 minutes more to do, but it's probably better to take a brief break. And I will either not cover everything or talk fast.
Thank you.
Hi, I have a question. So, is anything in your paper that is not included in your lecture notes? I was wondering. Because, I mean, I feel like everything is...
Oh, there's a lot in the paper that's not there.
Oh, okay, so this is even more complete than the lecture notes?
The paper is, yeah, and you know, amongst other things, it gives you details about, let's see, is the paper, this is the paper, right?
Yeah, this is the review paper.
The review paper. So, it tells you how to calculate, it goes through and does some calculations and gives other examples that I haven't had time to give here and so forth.
Okay, so this is even more detailed and more complete.
More detailed than, yeah, if you're...
Yeah, the last one I was involved in, so I didn't know.
Because I think that the registry it's not part of the registry.
question about these conglomeratics.
Mm-hmm.
So were you saying that if you cut this upper boundary, or you cut this two for each?
So what you should think about is this thing is closed on a torus.
Yeah.
And those two bonds connect this part of the torus to that
To
part of
this
the
one,
torus.
so that you
And then
have
when you
here
cut
the
that, it
equal
actually
number of-
separates out and becomes a
You have the
strip.
number of
Right. So the number of bonds I've cut to remove this strip from the periodic boundary conditions is 2 per
same
unit
here.
cell.
Yeah. Is it the same here and here?
No, here it's 4 per unit cell. So the unit cell gets squished down. The surface unit cell depends upon what the reciprocal lattice vector defining that thing is. And so in this case, there are 4 that are cut, and you can see those are the 4 that
Yeah,
are cut. Right.
1, 2, 3, 4. Yeah.
Yeah.
And here there are 2.
Right. And then you could then go on if you want, and you see these dotted lines here. You could cut those 2 bonds and that site as well. So you would be removing 1 more site and 2 more bonds, but that's like removing none, and that makes the top surface then look like this bottom surface.
Exactly. So do you also have the negative part for kappa here, or because I said
No, here I have the negative part. So
You have
for
also
this
the
one,
negative part, okay.
for this one, since it's the same, I didn't show
you
it.
didn't show it.
Yeah, it's a reflection about. I just reflect that down there.
Oh, so for the it is like this one and this one.
So this one is for these surfaces,
Yeah. I
and
know.
this one is for those.
this one.
Yeah, right. Mhm. It's all in the review article. Look at that. Right. Okay. Is everybody here? No. Well, your poor colleagues will lose out on gaining knowledge. Okay, so the theorem, this is so you look at a given surface, and remember in a crystal, you characterize the surface by the normal to it and by the reciprocal lattice vector that's associated with that. So, the simplest one is the surface along the x direction, which has a reciprocal lattice vector in the y direction, or maybe in the y direction. But in principle, I could take it along any cut. And as you do that, the nature of the unit cell along the surface gets more and more complicated. So I won't do that arithmetically, but that's true. And so we want to look at this quantity, which is the number of zero modes on the surface minus the number of states of self-stress. As a practical matter, in all of the examples we're looking at, this is equal to 0. So this is a statement about the number of zero modes on the surface. Now, you might expect that there's a way of dividing this up, at least rationally, into 2 different parts. Because we have one part that's telling us that we have to obey the Maxwell count, and another part that has to do with the topology moving one side to the other. So we break it up into what we call a local count and a topological count. Now, the topological count is simply the reciprocal lattice vector associated with the cut, dotted into a vector, which we calculate using the same technique which we talked about for the one-dimensional model, divided by 2 pi. And this RT, which you can think of as a polarization, is 1 over 2 pi I, integral along a contour that takes you between 2 equivalent sites in the Brillouin zone. So, for example, if you have a Brillouin zone that looks like that, I can go from here to there, and that's like going around a circle because this point's equivalent to that point. Or I can do that, or maybe I have a more exotic angle, and I can do something like, well, I have to be more careful about the definition of the Brillouin zone when I do the other G's. So let me not confuse you with my not getting the line exactly right. But you go between equivalent points in the Brillouin zone. No, it doesn't have to be a straight line. In this case, now there are cases which I probably won't get to where you do have to worry about that, where you actually have additional zeros in the Brillouin zone called Weil points that make the thing a lot more complicated. But we'll ignore those for now. So we need a mapping from here, from the Brillouin zone, to the complex plane. And what we do is we take the log of the matrix Q. Now, we could have done, it just turns out that historically when we first did it, we did everything in terms of Q instead of C. Obviously, I could manipulate things around and do things in terms of C instead. But we're going to take the log of Q. So this, and then I'm going to take the trace of this. Remember, Q is a matrix. I take the log of the matrix, and I take its trace, and then I have a number. And that number is a complex number, so it's a mapping from reciprocal space to the complex plane. And then I do exactly, I take the surface, this line integral, dotted it into the gradient with respect to q along that direction of the trace of the log of q, and that gives me a number which counts the number of, actually what it does is it counts the number of zeros minus the number of poles in that along that line, right? If I go along that line. And it turns out the number of poles are important in this case. They were unimportant in the one-dimensional case. So, yes?
So if that number is complex, don't you just
I need the, yeah, there's an imaginary part. Thank you very much. Yes, there is. I left that out. There's, no, this is, yeah, but remember that this thing will have zeros. I have an e to the iq. I still have things like that. And I'm integrating from q equals 0 to 2 pi. And then I just count the number of zeros that come out of that. So I don't have to put the imaginary part because the statement is if I integrate this function, which is a complex function, around a loop, this integral counts the number of zeros. If I put here, yeah, no, I think you're right here. I think you're right. I need to put an imaginary part right here. No, now you got me totally confused. Totally confused. What is the answer? I think I don't have to, but let's leave it for now. Otherwise, I'll stick my foot in my mouth. Right. I mean, if I write q is equal to e to the I phi, then I take the log of this. I get an imaginary part in the phi, which is canceled by that guy.
It's because I think before you define z, we just put the e of q.
Yes. So that I, right? So if I take the log, if I say q as an e to the I phi, then I take the log of it, I get I phi, and that I is canceled by that guy. Okay? Okay, so now, I mean, this looks like a simple operation to do, but there's a subtlety. And the subtlety is that these numbers depend upon how I've chosen the unit cell. And so I've already told you that, look, I can take the standard unit cell, which was, the one I showed you here. Oops. This one. So if I take this unit cell, which is the natural one to do, then it turns out when I calculate q, there are poles in z. So we calculate a number which is the number of zeros minus the number of poles. When I calculate the surface one, because I'm only going in the forward direction, I don't even have any back ones, it's only a function of z, and they're only zeros. So it depends on which unit cell I choose. And for the case of the Kagame lattice, it's convenient to choose the symmetric unit cell, and that's what this polarization is. We choose the q to be the symmetric unit cell, and then that's the polarization. Now I have to tell you about this. This you calculate in the following way. We start off with, say, a unit cell that looks like this, and I'm going to assign a charge plus 2 to each of the sites, and a charge minus 1 to each of the bonds. And that gives me charge 0. Now, for those of you who are in Mike Thorpe's orbit, this is very similar to what you do when you do the Pebble game in order to keep the count straight. So this guy has 0 charge, and it turns out that it also has a 0 dipole moment because everything is symmetrically located. But when I go to the cells on the surface, then what I have to do, for example, to create which is a good cell. What I need to do is to go back and look at this cell. So, you can see that the original cell was, say, this triangle with this bond, that bond, and this bond. And in order to get to here, what I've done is I've lost the bond that was coming down. There was a bond that was coming down here, and it's coming out. Let's see. Let's look at the triangle that's looking like this. There was a bond that was coming down like that. And what I did to go from here to here is to move this bond from there up to there. So I started off with something that had 0 dipole moment, and I move a charge from here over to there, which is a lattice spacing. So you can assign a charge to this guy, or a displacement vector, or something that has the same form as this RT. I should have said that this RT is right. So here, okay. I need to do this along the different directions. And when I do it along the different directions, this turns out to be something in the form Ni, Ai. And so I should have added one more thing. So I want to look at the particular directions in Q space, which are dual to each of the lattice vectors. So these are the lattice vectors telling you how you translate to get the same thing back, and associated with each of those is a complementary reciprocal lattice vector. So I should have put here that this is over a CI along the direction of the G that's going normal to that, and I get a vector which is actually a vector in the lattice. And you can get the same thing here by noting that you can move charges and bonds to go from the symmetric unit cell to the one that matches that. And that dipole that comes from that transition is an RL. This is the dipole surface, or the surface dipole. Okay, so now we can go and look at this. So here the safest thing is, this may be where I think I'm going to, I forgot to include all of the details here. So let me just say that, this surface thing, for example, I had to move the bar 6. So the original unit cell was this guy, this guy, this guy, all of the dark red ones. And then there was one here that I translate up to there. And that corresponds to a translation through a lattice vector in that direction. So here, this is a lattice where RT is in this direction. Notice that it's along the distorted symmetry axis. The reciprocal lattice vector is that direction. And when you go through this count, you find that there are 4 zero modes on this surface. And here they are calculated. Those are the penetration depths. One of them, now this guy is not this twisted Kagame lattice. It's one of the topological ones. And the one that goes to 0 does not come in with a straight line. It comes in with a 0 slope, and that has to do with the fact that the spectrum at low Q is different. Here's a case where I have 3 surface modes on one side, 1 surface mode on the other side. And here's a case where I have 2 surface modes on one side and none on the other, because this is one where I have to have a total of 2. So you can see by distorting the lattice, we can take a situation where we have a 0 mode on each side and move it to the other side. And now I can put them together in the same way that we discussed with the one-dimensional model. And the total count then is the difference between the topological count on the left and the right, dotted into the G vector that characterizes the domain wall. We've lost the local part here. And so when we close this calculation was done under periodic boundary conditions. Under periodic boundary conditions, the number of states of self-stress has to equal the number of 0 modes. So if I have a domain wall that has a 0 mode, under periodic boundary conditions, on the other side I have to have a domain wall that has a state of self-stress. And indeed, you can see. So this is a calculation of the full spectrum. This was done for that Hamiltonian that has both the Q and the Q transpose in it. So we have the up and the down ones. And you have these zero modes here that go along. This is the zero mode that we're talking about for every Q, except it comes up and seems to have a finite energy here. And that's because, in this case, we have a system that is finite in size. So when you go to low Q vectors, the penetration depth is much larger, and the wall sees the other side, and you get the energy raised. Actually, I should have, well, I won't waste my time. Yeah, I mean, all of this is certainly linearized, and I'm not, you know, even some of the surface modes that we looked at, I think some of those are also, if you try to go beyond linear order, things funny go wrong, I think. Now, these results here we can get in the same way that I discussed with the one-dimensional model. If I put a cut here, I can count the number of zero modes going this way, surface modes, a number of zero modes going that way, and then I have some glue that ties them together. I then have the number of degrees of freedom I have are the number of sites in the glue, and then the number of modes on this side, the number of modes on that side, and then the number of bonds and the number of bonds in the glue, and you can go through and do a count, and you can calculate the number of zero modes that you would have at a boundary. And it turns out here that you can actually create one of these things that has 4 zero modes at the boundary and nothing else, if I did the cut in this direction instead of this direction. So I don't think there's much hope that you can digest all of this in the 20 minutes we have, but you know, you should get a feeling that we know how to calculate, identify zero modes. And remember, we're only looking at zero modes now. If we looked at finite modes, then it's more complicated. And that there's a topological component that comes from this kind of an integral. But really, things can be more complicated. So if we go back to these lattices, for example. So this is now the analog of the distorted Kagame lattices, but it's from the square. And if you look at the spectrum of these things, there always are what we call, there are isolated zeros in the Brillouin zone that you can't get rid of. There are Weyl points, and around which, if you do an integral in the complex plane, you get a non-vanishing winding number. So that means that the polarization is not uniquely defined. As you go along the surface, you can see that the number of modes as a function of the Q vector along the surface change because you have these extra zeros in the thing, and that depends on the angle that I make the surface. If you look at this lattice in 3 dimensions, it's full of Weyl modes, these extra zeros in the lattice, but rather than being just isolated ones, they actually are lines of zero modes. So if you think of in 2 dimensions the Weyl modes as being a vortex in the reciprocal lattice plane, when you go to 3 dimensions, that vortex becomes a vortex line, which is why you have lines of zero modes. Well, the lines, we had some lines that twist, but with no knots, if that's what you're after. No, though I guess you saw circles that closed, didn't you, in one of your things, and that's also seen in the topological insulators, the closed thing. In this particular case, what we have are lines of zero modes that go, to the edge of the zone. So this says that there is still a rich set of parameters that we haven't fully understood on all of it. If you look at this lattice, this is a rational approximate to a quasi-crystal. It's nearly random. It has, on average, 4 bonds per site. And if you take the limit where you go to a complete quasi-crystal, you have something that is elastically isotropic. So this, if you now take and randomize these positions a little bit, it's a good model for a jammed system. And it turns out that all of the properties of this system are almost identical to what you get for a jam system. Now, this is a rational approximate, so you get it periodically repeated in all directions, and you can ask, what are the properties of that? And it turns out that this guy is full of Weyl modes. But it also has the property that if I just look at q equals 0, which means I'm looking at this cell alone, that depending upon how I randomize these sites, or in the case of jamming, depending upon how you, what particular structure you've created in your jamming process, you get a different number of 0 modes on this side than that side, which is an indication that they sort of have a topological character to them. Mm-hmm. Well, we have, yes, you can. I mean, it's corner shared tetrahedra. And in the plane of the triangles, you have a Kagame lattice. And so you move forward in the Kagame. So you distort the Kagame things sort of along the rules we have. And then you have this other triangle coming up, the other 4 legs coming up, and you move that guy around. And depending on how you move that, you get different behavior. Yeah. But and you connect them, right. So if you, yeah, I mean, so if you look at this, you can see the Kagame here. Here's a triangle, 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 triangle. And then they're connected like that, alternating. And actually, this guy introduces complexities that we don't have. You cannot define a unit cell with a 0 dipole moment. At least we've not succeeded in doing so. Right. OK, I think that I've covered everything that I had intended to cover, though perhaps more rapidly at the end than we should have. But I've come in at exactly 10:28, and I want the director to compliment me about that. OK. Questions? Good. I've snowed you completely. Yeah.
I've only ever heard Weyl modes discussed in the context of
Yeah.
mechanical.
So we're developing that now. We don't have a full control over it, but so they do have interesting properties, particularly when you go to the nonlinear stuff, which we're working with. Vincenzo may talk about this a little bit. I don't know. You're going to mention? Yeah, he's going to look more into nonlinear. But certainly, you have a finite wave vector bulk 0 mode, and you can ask what effect that has. And it's complicated. It's not. Truth be told, right? What I've been looking at is a model lattice, which is very hard to see a real physical realization of. We have these Maxwell lattices where we only have nearest neighbor bonds and sites, and it's almost impossible to make that for real in the real world. You can come close with that picture I showed of the compressing of the system, but there's still some bending forces. So, in a sense, right now this is intriguing mathematics. And there is a question of what will survive beyond the intriguing mathematics. Oh, there was one more thing I wanted to show. Maybe this will just end the picture. So I told you that we have Weyl modes that are not Weyl modes, but guessed modes that depend upon how I've destructured the lattice. So here I have can you see that? I have a glider now. So this is the standard Kagame lattice, and if I squeeze by a factor S on the bottom, it does just what I said. Now I'm going to start distorting the lattice. Let's see, let's do this like that. It does sort of the same thing, but now let me do this one like that, say. So they have all kinds of funny Weyl modes, which are representative of the exotic structure. So this part of the analysis, I think, is going to survive adding next nearest neighbors and things like that. And you can also ask, as I perturb away from it, I mean, can I have a situation where the next nearest neighbor forces are small? And indeed, there are lattices, I forget what they're called now, the ones that they use for making filters and things like that. These very open lattices that have a lot of freedom to move tetrahedra around so that you know that the bending forces are pretty small. And so this might be a starting point to tell you what goes on there. Yeah. Yeah. Yes, yeah. Yeah.
For example, I hope you make lattice like this.
Mm-hmm.
It's true that there are bending forces with the torque, but then say that you make your beams,
Right.
Then there's only one elasticity that becomes much more important. Yeah.
Yes, right. That's what I mean.
Your predictions are extremely.
So you've made them with really thin wires? Yeah. Okay, good. Yeah. Yeah.
And as you expect,
Yeah.
there's always an hierarchy in there.
Right. So I think that in these meta artificial structures, which is more and more popular these days in material science, you will be able to see that. But if I go and look for some solid that I pick off the shelf in the lab, it's unlikely. But I think that yeah, but it's costly enough that it gives a big gap most of the time. I mean, it's not a trivial correction. I mean, it's big enough. In fact, it's amazing how little bending force it takes to give you a pretty big gap. I'm surprised at that in our calculations. Yeah. But you might say then, well, graphene would be a good one. So graphene has the property, if there are no bending forces, it has a plane of zero modes, and you add the bending forces, and then you bend it off. And you can actually, if you add next nearest neighbors to that, there's an interesting, randomly distributed one. You get a transition that looks like a jamming transition. So there are things to do, and Vincenzo is more the optimist than I am. But I think we will see more and more of these artificial structures being made. And you can ask questions like, suppose I construct something where I build in a very weak domain wall and make a lattice of those. Then what kind of macroscopic mechanical properties will that have? Are you interested in making something where you have a weakness at a particular point? Or you can take these Kagame lattices and you can change the size of things. So when you compress it, you can end up with a distribution of different hole sizes in well-controlled positions. So it might be a good filter or something like that. So I think that we will see, at the micron scale and perhaps at the submicron scale, you might see some interesting things being made. Okay. More questions? Tea time.
Sorry, I have a question.
Good.
So in these networks, you said they have a behavior near jamming.
That's similar. So if we calculate, if you take the point of view that jamming is defined at the point where z is equal to 2d, this is a lattice that exactly satisfies that.
Okay.
Okay, and then you can ask.
Is that the only thing that is similar to jamming?
No, a lot more. Okay, so if I look at this.
What about the shear and?
Okay, so all of that works. So if I look at this guy alone, then it has lots of states of self-stress, these things right here, that give me zero modes that you don't see in the jamming. Okay, but then if I go along and randomly displace all the sites, then I get something where the bulk modulus is finite, and the shear well, now this thing is a finite size, so there have to be two shear moduli. One of them has to be zero by the guessed mode count, and the other one is non-zero. But if you make the thing larger and larger, it approaches an isotropic limit as there's jamming. So the second shear modulus, which is finite for the small unit cell, goes to 0 as 1 over n, which is exactly what they see in that. If we look at the normal modes and the density of states and all that kind of stuff, it all is almost identical to the. Yeah.
So I work with Michael Thorpe.
Yeah. Yes. Yeah.
So we have been constructing kind of networks.
Yes.
That, we start from some amorphous,
Yeah,
totally source
right.
networks, and we dilute it by imposing the Hilbert stability condition. It's just a geometrical condition. And as you can see here, at all the sites, the Hilbert condition is satisfied. Even in this
The Hilbert condition, remind me what that is?
So Hilbert condition says at each site, if you imagine, if you draw an imaginary circle, you can't find any semicircle that is empty.
Okay, yeah,
Okay,
right,
so-
yeah, okay, so this
So
is
that's a
this is a
geometrical
dense system in that sense, right? And yeah, and that's why
So the networks we were able to build showed some properties of the jammed networks, but we haven't measured the bulk and shear modulus because, well, we're waiting for our collaborators to measure it. But I was wondering if, like, there are other ways.
so you're working
to,
with it with a group in Leiden,
Yes.
yes, with
But-
Voter,
Yes.
Voter, yeah,
Yeah.
okay, yeah, I know.
So, but they said they don't have the program for it because they have to do the molecular dynamics for it. So
No, this we just do by conjugate gradient. We do exactly what I said. You impose a uniform shear on all the sites, and then you fix that, and then you relax them by conjugate gradient, and you get the elastic
we
modulus.
have been having problems with relaxing also.
I see.
because, we can't get the cost that
What
nice as Mike is looking for. So, I mean, we can do it with finite networks, but when
The networks become
periodic
large.
conditions, we
well,
just don't
we-
get the cost. So the minimum of the energy is just like a very wide thing. It's not a
Okay, so we went to, I think we went up to 10,000 sites and didn't have any trouble.
So yeah, our networks are really small.
Oh, so
They
for
have
the
like
small ones,
400
for 400 we had no trouble at all. In fact, with 400, we did those on Mathematica.
Oh, okay. Will you have time to send? Like,
But now I have to tell you that the numerical stuff, that's my postdoc's domain. I mean, I want to just.
No.
So I can't tell you about the details, though. If you want to contact him,
Yeah, sure.
you can do that.
Yeah, that would be great because
So, okay, and then in addition, there is this question of if I take this guy and I imagine now making a half plane that goes like that, and I can count the number of zero modes per unit cell here, and what we find is that there are different number of zero modes on this side than that side that depend upon how I randomize. And the jammed lattices have that identical property. So we're writing
yeah,
that
so
up now.
that's one of the things that we can do in our networks.
Yeah, right.
Okay.
So I mean, I think that these networks that have average coordination equal to 2D that are, as you say, sort of reasonably dense, my guess is that they are going to share something. Now, there's some slight differences. It takes longer for our bulk modulus to saturate, but all of the other properties, and that's in the PhysRev letter that's cited in there with Olaf.
Yeah. So yeah, we have measured some stuff like we
Yeah.
have two indices, S and H indices, if you're familiar with that.
S and H indices.
So
No,
we
I don't
start
know.
with the totally isostatic at
Yeah.
z equals 2d,
Yeah.
and then we add one bond and we count the number of stressed bonds.
Yeah. Okay.
So
So
in the jammed networks, it's one because when you add even one bond, everything turns stressed.
yeah. So we do that also. So you look at it if you have exactly z equals 2d, then you have to have two non-zero elastic constants, except when you go to this isotropic limit where you have this extra thing. And so we've removed one bond and found that all that survives is the bulk modulus. And if you remove two bonds, you have nothing left. Now, of course, what you're talking about here is you're viewing this guy as your whole sample.
Yeah, kind of.
And
yeah,
you know
so-
what we can do, and also
But
with the
it's
jam system.
periodic.
Well, but if you make it periodic, then you're allowed to say, well, what happens if I actually treat this as a periodically repeated unit cell? And then you can put in the wave numbers. If you do that, you get lots of Weil points and things like that.
Okay, so who's your postdoc?
It's Olaf Stendel. I'll try to find his email to
Okay,
and send it
okay,
to you.
that
So
would be
you're
great. I'm
Hugh.
Varda.
Varda Ha. Okay.
Hug.
Hug.
Okay.
Hug. Not Hach. Yeah, okay.
Okay,
Yeah.
thank you so much.
Right.
So I wanted to ask for that integral that you wrote
Yeah.
when you map to the
Right,
complex plane.
right.
Is that related to the Chern number?
Well, it's like the Chern
It has
number.
the same flavor, right?
Yeah, it has the
But
same flavor.
is
It's. I don't think it's exactly the same, but
what's
it's.
the difference?
Well, the Chern number is often used for higher dimensional things. So here we have really a map from one point simply to the complex plane, which is a two-dimensional thing. When the Chern number stuff often is mapping to a surface, a three-dimensional thing, or you have a texture and things like that.
But qualitatively.
Qualitatively, it's similar.
Same.
Yeah,
Similar.
similar. Right,
Okay.
right. And there's more that can be done in that direction, which we just haven't had time to do
You
yet.
mean to relate
To relate them, yeah,
constants?
right. I have to say I don't fully understand all of the the electronic topological
I
stuff
don't
yet.
either. That's why I
Well,
was
I
hoping
just
that
have
that's what it was.
it's an impenetrable literature that requires a little time, and I've just taken time to do this instead of studying that. Yeah.
I don't know. I guess I just had questions about kind of. Well, I wanted to ask a question about this paper. So when you do this, you kind of take the square root of so you make this Hamiltonian thing. But is there any actual reason to do that besides the fact that you kind of make this analogy where you have like positive?
No.
And
So
negative
if all you're
things?
interested in are the phonon properties, you don't have to do that. But you do have to be able to talk about the equilibrium and compatibility matrices separately, because they are the ones that contain the topological information. So I don't have to do that.
Yeah, because it seemed like even when you calculate the topological thing, that you don't even use the.
We don't know what. So
you use the compatibility.
So
matrices.
if we had surface states with states of self-stress, which we could, I could go in and doctor up the surface. So it had a state of self-stress, and then we would have to keep that in that count.
Okay.
But we haven't put that in. So the theorem is, the theorem that I wrote there is actually derived based upon the square root part.
Okay. Yeah, but the square root part is the compatibility.
It has both of them. And so the technology for calculating those things is really works better on this matrix. So you have these things about particle hole symmetry and all of that, which you can't see if you just look at the phonon part.
Okay.
So by doing it that way, you're able to bring to fore all of the the powerful formalisms that the topological electron people have used. And I don't know if you looked at the supplementary material on this, the derivation of that thing is not at all transparent.
Right.
I mean, it is it's a challenge for someone who doesn't do quantum physics regularly.
And then another thing, I guess, is like, so we calculate this topological invariant.
Right.
But so how do we think? So we think about this as kind of like a mapping from.
It's a mapping from the Brillouin zone to the
complex
complex plane. Yeah.
And then just the number that you get, kind of. I don't know how do we
So
think
the
about that
the number
exactly?
we get is something that tells you how you've transported zeros from this side to that side, really. So if you think of the one-dimensional case, right, if you have n equals 1, you're decaying this way, n equals 0, you're decaying that way. And now in the two-dimensional case, you have a vector that tells you what surface you're talking about. And if you have a topological lattice, it will take a case where you have the two zero modes on this side, and it'll move it over to that side or that side, depending upon what that RT.G is. So the RT.G is like the one-dimensional end. I better get out of this gentleman's way here quickly. You can just take. Thank you this time. Yeah.
Thank you.
Good. Yeah. Thank you. Yeah. Let me just get this out of the way here, and then we can. Put this here for a second and put things away. Okay. As I'm putting this away, you can fire your question.
So I guess a lot of what we've been talking about so far is like local deformations of the crystal.
What do you mean by local?
Just like the harmonic approximation.
Oh, well, it is the harmonic approximation. Yes, that is true. Yeah.
So I was wondering, so like certain statements, at least in the preliminary statements, at least, can be kind of generalized.
Well, yeah. So there are the nonlinear stuff is actually not too well codified. Vincenzo will talk about some aspects of that, but even if you go to the engineering literature, they identify what they call finite mechanisms as opposed to infinitesimal ones, but they don't really have a general algorithm for knowing when it's finite and when it's not, and so forth.
Or if perturbing along a certain, I don't know, if you're looking for states of self-stress with finite deformations.
Yeah.
Do people know when you'd be able to kind of find finite deformations without kind of creating an instability or something?
Well, the answer is that for particular cases, people probably know a lot. I haven't gone through all of that literature to be sure. A general statement of the generality of what I've been talking about for the linearized stuff is not available to my knowledge. But you can take the lattices we have, and you have no freedom. You remove all of the boundaries. They have, they have square root of n degrees of freedom that allow you to distort the thing in all kinds of cockamamie ways, right? So I've focused on the ones that are nice and beautiful. But if I came along and told you, well, I'm going to give you a particular shape of the bottom surface and ask what the thing looks like far away, what happens pretty rapidly is when you get way out there, you start having bonds intersect and things like that. So I don't have a good sense as to where that's going. In the one-dimensional case, Vincenzo has it down pretty nicely. It becomes, you can put it in a form where you actually make models and see the nonlinear thing. In the higher dimensional case, I think that's territory that remains to be explored. So, but if you like it and go in that direction, be sure you read the engineering literature. There's a lot out there. Yeah. So, are you working on that kind of stuff, or not at the moment? Okay. Yeah. Good.
I just wanted to show you a picture
which
that's kind of used me recently. And so, do you see these threads of lines? Which
yeah, right.
Connected through the boundaries. This is actually a experimental sample of silica glass. And I think these lines through the boundaries are almost the equivalent of those straight lines in Kagome. Because,
right. Except that they will not by themselves support a state of self-stress. You need the other. Yeah. Okay. Right. So. Yeah.
Sometimes we have this.
But it's still fourfold coordinated everywhere, isn't it?
Yes.
Yeah. Yeah. Interesting.